Alright guys, so for today we're starting 3.5, implicit differentiation. Like I said, some of you guys probably can't see in the back, so move forward. Okay, there's plenty of room up here. First of all, what it means to be implicit. I need to make sure that you understand what that is. So an implicit functions are functions in which no variable is isolated. Okay, so that means that you can have variables on both sides. An example of what that is like this one that I have here, x times y equals to 1. That's implicit. Do you see how both variables are on one side? Okay? So that means that not one variable is isolated. Question, could you isolate the variable?
Yeah.
You could, right? And that would be an explicit function. But I'm going to show you what would happen if you're not able to do so today. So here are the steps that you need to do in order to solve implicit functions and how to differentiate them. The first thing that you got to do is you got to differentiate both sides with respect to x, and that's very important. You are differentiating with respect to x. Now, if you don't know what that means, I will explain that here in just a minute when we do an example. So, with respect to x. Step number 2 is you're going to collect all the terms that involve dy dx. Again, if you don't understand what that means, we'll talk about it here during a problem that we do. And move everything else to the other side. Okay? You're going to factor dy dx, and you're going to solve for dy dx. Now, what does dy dx mean? The derivative. And it makes sense that we want to get dy dx by itself so that we can say, hey, the derivative is equal to this. Now, if you're completely confused of what I'm talking about, like I said, just stay with me. We'll do a problem here in just a second. So if you're watching the video, I'm going to pause this so I can let my class write down the steps, and then I'll hit play here in just a second. We're going to differentiate the very first example that I give you. Here's what I want you to do first, okay, before we even start doing implicit differentiation. Solve this using the rules that you know. In other words, can you solve for y here? Yes? Okay, solve for y. So if we solve for y, what is this equal to? Y equals 1 over x, right? Now, if you see that problem, we could even go a little further and say that y is equal to x to the negative 1 power, right? Using knowledge from previous lessons, you can find the derivative of that. So what would the derivative be equal to? Negative 1
over square root
x to the negative 2, right? Which we can clean up to be negative 1 over x squared. Agreed? And we know that's the answer. Now, the reason why I'm asking you to do this is because I want you to compare what we're about to do with implicit differentiation, and which you still be able to get there, okay? I chose this example not because we need to use implicit, but because I want to show you an easy example in which we can use implicit. Okay? Now, in order to use implicit, that means that we're not going to isolate a variable. Okay? That means we're going to leave it just like it is. Alright, so we have x times y equals to 1, right? Can you guys all see that this is a product? You have x times y. So we are going to do the product rule. Now, the product rule says take the derivative of the first, which the derivative of x would be 1. Bless you. Agreed? And then you multiply by the second term, which in this case is just y. Agreed? Plus, you leave the first term alone, which in this case is the x, and you take the derivative of the second. Now, so far in the class, you have not taken the derivative of y. Agreed? You've always been taking the derivative of x. Well, remember how the instruction says, take the derivative of with respect to x? Well, that's not x. So in order for you to show that you're taking the derivative with respect to x, not only are you going to find the derivative of y, well, the derivative of y is just going to be 1, right? If you think about it. But because you're taking it with respect to x, you must follow it with dy dx. Now, why do I put that there? All year long, technically, you have been doing this. You just never had to show it. I want you to think about this. And I'm going to go kind of on a tangent here on the side. When you had, for example, x squared and you took the derivative of that, you did 2x. What you did was the following. You just never needed to write it. Dx over dx. Do you see why you wouldn't need to write that? You took the derivative of x with respect to x. Dx over dx is always just a 1. So there's no need for you to ever write that. However, because you're not dealing with x, it's not going to go away. That dy dx will stay there. Cool? That is equal to, well, you got to take the derivative of the 1. What's the derivative of 1? 0. What does the steps tells you to do next once you do the differentiation?
Factor dy dx.
Isolate dy dx, right?
Oh.
We need to factor it and we need to isolate it, okay? So first, can I subtract the y and take it to the other side? So I'm going to have x times dy dx is equal to negative y. Agreed? Yes? Lastly, you need to just have dy dx by itself because, again, dy dx is the derivative. That's what we're looking for, right? So dy dx is equal to what? Negative y divided by x. Question. We did this earlier. How come this is not the same as that? They should be. They need to be. We know, like, we are 100% sure this is correct. So why is this not that?
Oh,
What do you, hold on. What do you think, Zach? Hold on. What do you think? How are we going to manipulate it? Right, but I need it to look like this, though. I need this to look like that. Okay? Jada, what do you think, man? No? Pranav, what do you got, man?
y equals 1 over x. You just plug in 1 over x.
Cool. Guys, go back to the beginning of the problem. Couldn't we rewrite this, and we did it previously, 1 over x? So, you know what y is? Right? Can I take that and replace it to there? Right? It's equivalent, right? You guys with me? So what that means is that I have the following. Negative, what's y? Well, y is 1 over x. Agreed? All over x. Now if I play around with that, wouldn't that be dy over dx is equal to negative 1 over x squared? And isn't that exactly that? They're exactly the same. Cool? If, and I'm going to put a big like star on that, if you know what y is, you need to replace it. You won't always be able to replace y. And I'm going to show you examples of when we're not going to be able to replace y. Okay? The reason why we were able to replace y here is because there was no reason for us to use implicit here. Agreed? Like, that was a lot more work than what we did on the right-hand side. Anytime you have a function and you can rewrite it as terms of y equals something, do it and use your rules. However, if you cannot do that, you're going to have to use implicit. Can anybody think of an example when I'm going to have a function or some kind of equation in which I'm not going to be able to rewrite it in terms of y equals to something? What do you got?
Oh, when it's like 2 to the y.
Okay. Okay. So you kind of created a problem. That's fine. What do you think?
If you have two variables that are changing, like, say you have something like that's on a wall that's sliding down, both the y value and x value are changing.
Cool. So now you give me a word problem, right? What if I was interested in what's happening to the x and the y at the same time, which is actually our next lesson? Thank you. We can talk about parametrics, but we're getting a little ahead of ourselves. I want you to think this through. Let me remind you, conics.
Oh.
Do you remember conics?
Nope.
Ellipses, circles, hyperbolas, parabolas. None of those none of those equations you could rewrite as terms of y equals to something. Do you remember that? Well, here's the
They're not functions.
exactly. So here's the thing. The beauty about calculus is when I told you that you could differentiate, really one of the requirements, one is that it's continuous, right? Never did it say that it had to be a function. So what if we have something that's not a function? Again, like a conic. A conic is not necessarily a function. So we're not going to be able to isolate y, therefore we must use implicit differentiation. And that's the reason why this exists. Cool? So now can we move on to problems where we're not going to be able to solve for y?
Yeah.
Yes? Yes, sir.
Wait, okay, so let's say you have a circle, right?
Right.
And, like, you want to take a limit of it, then what would you...
You're going to have to split it into the half of the circle, right? So that you can have... Exactly. Cool? All right, very good. So next example. Example number 2. Let's start out with y to the third power plus y squared minus 5y minus x squared is equal to negative 4. Okay. You don't need to figure out what this is. You don't need to graph it. There's no need for you to do all that. Okay? But I hope that right away you recognize there's no way that you can get this to be y equals something. Question, could you have this be x equals something?
Yeah.
We could. And could you differentiate like we've been doing before?
Yeah.
We could do that. I'm going to be honest, that's probably going to be a lot more work. Don't avoid implicit differentiation. It's relatively simple. Ready? Okay. What is the derivative of y to the third power?
3y squared.
3y squared what?
dy.
dy dx. Do not forget your dy over dx. Plus, what's the derivative of y squared?
2y given it.
2y times dy over dx minus
Minus 5 minus
5 dy dx. Again, you're dealing with y. Cool? Minus what?
minus
Does that need to have a dy dx? No, that's already with respect to x, right? Is equal to what?
0.
0. Cool? What do I do next?
You take all your dy dx terms and move them to one side.
Cool. Can I take a few steps in one, like in one? Are you going to be okay with that? Can I rewrite this as dy over dx times 3y squared plus 2y minus 5 is equal to 2x? Are you guys okay with what I did there? Two step in ones? What's your derivative? 2x over what? 3y squared plus 2y minus 5. Agreed? Question. On the last example, we were able to replace y. Are you going to be able to replace y?
No.
So no, we cannot. Is it okay for us to then have y in our derivative?
Yeah.
Yes. Now here's my question to you. What if I then have that and I ask you to find the tangent line? And I want you to find the tangent line.
Wait, you would give us an x and y then?
Find the tangent line at the point 1, 1.
And then you plug in the y coordinate instead of the x.
Fantastic. Yes, sir.
So that would be the final answer.
This is, like, if the question was just to derive it, this will be done.
That's
Right?
undefined.
So now, the second question is now, can you find the tangent line? Previously, all you really needed was the x coordinate. However, now you need x and y, which you do have. I provided for you. So if we want to find the tangent line, we need to evaluate the derivative at 1, 1. Now, to let the reader know that you're evaluating something at a point, here's how you write it. You ready? dy over dx evaluated at 1, 1. That's what that means, evaluated. Okay? It's like, I don't want to confuse you, but you remember logs, how you have like a little base? It's not a base, but that's just the way that you're letting someone know, I'm evaluating this derivative at this point. Okay? Well, if I do that, well, it's 2 times x. What is x? 1. Over 3 times y squared, so y is 1, so 1 squared, plus 2 times 1 minus 5. Agreed? Okay, 2 times 1 is 2. That's 3 plus 2, which is 5 minus...
Undefined. It's up, straight up.
So what does that mean?
It's straight up line.
It doesn't mean that you don't have a tangent line. It means that your tangent line is vertical. Because think about it. Which lines, horizontal lines have a slope of 0. But vertical lines have a slope that is
Vertical.
undefined, right? What is that line then?
Is it straight up and down?
But where?
Is the line at 1? X equals 1.
X equals 1?
Yeah.
Are you sure? Why at 1?
Because
That's where the point, it has to be going through the point that you want it to go through. Therefore, x equals 1 is the tangent line at 1, 1. And we're done. Cool? So now you're going to need an x and a y coordinate in order for you to find the slope. But everything else will work exactly the same like it has previously to today's lesson. Okay? Bless you. Alright, so then I want you to try the next one. The instructions from the beginning are to find the tangent line at the given point. Okay? So here's your problem. Example number 3. find the tangent line. And the line, the equation I'm going to give you is x squared minus x times y plus y squared equals to 7. And I want you to figure this out at the points -1, 2. Okay, I want you to try these on your own. If you're watching this video, go ahead and pause it and try it on your own. When you're ready, hit play and you will be able to check your answer. Okay, so check your answer. When I started taking the derivative of this, x squared, the derivative of that will be 2x. You have a product here, so I went ahead and put minus, and the derivative of this product ends up being x times dy dx plus y, or the other, y plus x dy dx, okay? Plus 2y dy dx is equal to 0. Kind of clean things up a little bit. I brought over everything else that did not have a dy dx term, so it's the y minus 2x or negative 2x plus y, however you wrote it. I factor out the dy dx and divide it by that, which means that that is my derivative. Agreed? Now, if I want to figure out the tangent line, I need to figure out the slope at the point, so I needed to evaluate it at -1, 2. Agreed? Which eventually got me 4/5 as the slope. Yes? If you have the slope and you have the point, then the answer should be y minus 2 is equal to 4/5 times x plus 1. Yes?
Wait, but the constant never matters.
What constant?
The 7? It does, like,
Yep. It will always go away. Because the derivative of a constant is always going to be 0. Now, on my other classes, I had them find the normal line. Do you guys know what a normal line is?
it's the force going up from the surface, but...
Okay. We'll talk about physics in just a second.
Wait,
But what does it mean to be a normal line? What does it mean in mathematics for something to be normal line?
Y equals x?
That's the identity function. A normal line, really all it means is the line that is perpendicular to this tangent line. That's what a normal line is. So you don't really need any calculus to give me this answer. How do you know, or how can you tell that something is perpendicular? Yes.
It has
They have an
negative
inverse negative slope.
Negative reciprocal.
Negative reciprocal
Inverse.
slope.
Yeah.
So if the slope of the tangent line is 4/5, what is the slope of the normal line?
Negative 5/4.
Which means then that your normal line would be that. Everything would be exactly the same, except the slope would be the negative reciprocal of the tangent line. Now, someone asked me, well, what's the value of knowing the normal line? Okay, so let's pause. You know the value of finding the tangent line, right? You guys remember that. We've been studying that for a while. Now, you kind of got ahead of myself, but tell us, please, why would we care about the normal line? In physics, it comes up.
I was just thinking.
I can make it,
Actually, well, but you were technically correct. Yes, sir.
okay, wait. So let's say, okay, if we have like a force,
Right, we're talking about forces here.
okay, so then that would be the tangent line if you add.
Okay, we have a force, guys, and I don't know, we're not going to get in depth. When you take physics, they'll talk about this. But there is a force, like just pretend you have an object, like this horizontally. There is a force acting upon that object that will go either up or down, which will be perpendicular. That's known as the normal force. That's why it's called the normal line. Now, in physics, you will need to take the derivative in order to find the normal force, right? You take the derivative, you find the slope of the tangent line, and all you do to find the normal force will be to get the negative reciprocal of that. You don't have to do that here in calculus, but I thought I would share it with you. Why not? Cool? All right. Very good. Ready for another one, or yeah? Okay. Let's try another one. A little harder? Okay. Sure.
Yo, everyone got confused on this one example, like.
I didn't get confused. I'm
Sample number 3.
That's true,
Okay. If x squared plus y squared equals to 25.
It was a circle. Radius
It's a
5.
circle with a radius of 5. Fantastic. Find the second derivative. Find the second derivative. You wanted something a little bit more difficult. It's not that bad, though. So we can do this together, okay? You know how to find more than one derivative, agreed? Okay, ready? Let's find the first one. That's where we got to start. Agree? Yes, sir.
Is there a reason you put the second in a different place?
That's how we write it. Yeah. So the 2 goes in between the d and the y, but the 2 goes after the x on the denominator. Okay? Alright, if we find the first derivative, you ready? What does the first derivative look like? 2x plus 2y dy dx is equal to what? 0. Agreed? Solve for dy dx. Tell me what the derivative is. Try it.
X over y. Yeah, negative x.
Agreed? The first derivative, so dy dx is equal to negative x divided by y. Agreed. Now, can I rewrite this for the moment as negative x times y to the negative 1? Can we do that? Are you okay with that? Yes? Well, if you want to find the second derivative, what are you going to do? Just, we don't need the chain rule, just the product. Right? Because, I mean, there's no reason to use a chain rule here. So, the second derivative is equal to, okay, if I'm going to use a product rule here, what is the derivative of negative x?
Negative 1.
So it's going to be negative 1 times what?
Y to the negative 1.
Y to the negative 1, right? I'm going to leave that alone. Plus what?
Negative x.
Negative x times what? The derivative of y, right? Which in this case is going to be negative y to the negative 2 times
dy dx.
dy dx. What's up?
No.
You're good? Okay, I know it doesn't look pretty, but we can clean up all these negative exponents, right? Agreed? The second derivative of y in terms of x is equal to, what does this become if we clean it up?
Negative y to the negative 1.
So negative 1 over y, right? Agreed? Okay. This will then become, is it still positive or negative? Well, negative times negative gives us positive, right? So plus what? X over
X over y squared times dy dx.
Cool. Agreed? That's where we're at so far. Here's the problem. You can't have this left over there. There's no way. Yes, sir.
Common denominator.
Yeah, they're multiplied. Yep. Because technically, remember earlier we had dx over dx, which is just 1, so we're still multiplying by the 1. So we are multiplying this entire, is it the entire thing or just this one? It's just this one right here, times that, okay? Now here's my question. You're not done. You can't have a second derivative and have the first derivative there. You need to get rid of this. So here's my question. Do you know what this is equal to?
Yeah, you plug it back in. It's equal to...
What is dy dx equal to?
Negative x over y.
Right here. You found it. It's right here. Agreed? dy over dx is equal to negative x over y. Right? So that means I have to go back and say the second derivative is equal to negative 1 over y plus x over y squared times what?
Times negative x over y.
Negative x over y. Have I lost anyone? Do we understand why the negative x over y is there? Yes? Okay, if I clean this up, the second derivative in terms of x is equal to negative 1 over y plus, well, minus this time, right?
Yeah, minus x squared over y cubed.
Minus x squared over y cubed. Now, looking at this, I know that most of you guys will probably look at it and be like, okay, I think this is good enough. I have a feeling that we're going to be able to do something else. I'll explain to you here in just a second why I have that feeling. Yes, sir.
Can we go higher?
Yeah,
What do you mean?
why?
So if we went higher, you would do it all again.
Oh, like if we wanted a third derivative?
Yeah.
Yes. And then you would have to replace not only the second one, but also the first.
Dude, why would you...
But,
Why?
okay, so pause. Stay with me. The reason why I think this can go further, it's because I'm seeing this negative 1 minus x squared, which makes me think of
Trig.
coming right back here at the beginning for some reason.
Oh.
Okay? Now, let me kind of go a little further, so maybe you'll see it. Okay? What if I get, instead of having two fractions, common denominators? If I get common denominators, the common denominator is y to the third power, right?
Yeah.
In order to achieve that here, you would get a negative
Y squared.
y squared minus x squared. The moment I see that, I'm even more suspicious that I can do something.
Is
It's equal to negative 25 over y cubed.
Hold on, dude. Hold on. Do you guys all realize that I can factor out a negative 1 from the numerator? Leaving you with y squared plus x squared.
Oh my goodness.
Yo, that's wild.
And right at the beginning of the problem, you know what x squared plus y squared is.
So we would have had to do that on the other side.
Therefore,
It's like geometry, we have to like draw imaginary lines.
your second derivative would be equal to negative 25 over y to the third power. Guys, every time you're simplifying things out, even when you took the quiz, I'm okay if you have multiple factors that are being multiplied, but when you have multiple factors that are being added or subtracted, you have to combine them, because then things like this can happen where you can cancel things out. Cool? Second derivatives, are we good? I'm not going to ask you to do anything further than a second derivative with implicit.
20 seconds.
The reason for that is, think about it. You only really need the first derivative to find the velocity of something, and the second derivative to find the acceleration of something. I won't go into jerk. I won't go into anything further than that. Okay? So the second derivative implicitly would be more than fine. Okay?
Our quiz is one question. Find the 25th derivative.
No.
That's like not the AB test.
All right. Last problem we're going to do implicitly, and then I'm going to show you a new skill. Okay? So example number 4.
Logarithmic differentiation.
Yes, logarithmic differentiation. Okay? This is the last one, and I want you to try it on your own. So differentiate. Let's bring in trigonometry. We haven't tried it, right?
Okay, but can you
4
put the table of
cosine of x
I don't want to do like
sine of y equals to 1. Try this one on your own. So if you're watching the video, go ahead and pause, and then when you're ready, hit play so you can check your answer. Alright, so if you're watching the video, here's the answer to that problem. We had to use the product right here. Okay, so the product of 4 cosine times sine y. Eventually, you were able to get here. Now, it's very obvious that the 4 cancels out, and sometimes some students will leave it as sine x, sine y, cosine x, cosine y. But if you have sine over cosine and they have the same variable, you're able to then simplify that into a tangent. Therefore, the answer for this would be tangent of x times the tangent of y. Okay? Any questions? We're good? Alright, thank you for watching this video. If you're interested in learning how to use logarithmic differentiation, then watch the next video.